Okay, good morning, children. Here we are again with chapter 6, heat transfer. We are continuing. I think this is the second time I'll be doing this chapter. Okay, now, till last time we talked about evaporation, effects of evaporation, the differences between evaporation and boiling. Now we are going to talk about thermal expansion. Okay, thermal means heat, and expansion obviously means to expand, to become bigger. So how does heat bring about a change? How does the heat bring about an expansion also? Okay, now most substances increase in the dimensions. Dimensions means in this, see in physics we talk about dimensions because we cannot say it becomes bigger, it becomes smaller. Okay, we have got many types of expansion also. We have linear expansion, superficial expansion, cubical expansion. This is why we have to talk about dimension. Dimension basically means the total area, the total surface area, the volume, the size, whatever of an object. Okay. So whenever a substance is heated, whether it be solid, liquid, or gas, there is an increase in the dimensions. There is an increase in the size, or it becomes bigger, a little bit bigger. Okay. Uh, most substances increase in the dimensions when they are heated. The expansion produced in matter due to the absorption of heat energy is called thermal expansion. Okay, that's what the book says. The expansion produced in matter, that means matter, anything matter. Matter is anything that you can touch, feel, see. Okay, so when it is heated and if it becomes bigger, that is expansion. So it's the expansion produced in matter due to the absorption of heat. Absorption of heat means when it is heated. As I've told you, heat always moves from a hotter body to a colder body. So the body is heated, it expands. Okay, that is called absorption of heat and expansion in matter. So what happens, what exactly happens out here is, when a substance is heated, the kinetic energy of its molecules increases and the molecule starts moving vigorously. Basically in a solid, let's say any solid, okay, you take a solid like this or a solid like this, there are molecules inside it, right? Right now the molecules are totally fine, nothing's happening because it's room temperature. The moment this solid is subjected to heat, right? No, the molecules inside, see, even in solids, though we do not see the solids moving. For example, if I leave this chalk here, right, and it stays here, perfectly camouflaged with a white background, and it's undisturbed, and let's say weathering does not take place in this chalk, that means it does not become smaller or it doesn't get broken down, anything else, nobody moves it. If you leave it here, if I come here 10 years down the line and nothing has happened to the chalk, I'll still find the chalk here. Okay, so we tend to say solids, like objects don't move on their own. So many physical, not physical, theories of physics are there. All those things are there, right? So it will not move if I leave it there. Rest, motion, all those things comes, right? So what I'm trying to tell you is, do we think that solid is a block of thing where molecules are static, it does not move, it's placed in one place? That's not true. The molecules inside the solid, they are in motion, but the motion that they have is vibration. They are vibrating. Understood at one point in time. So the moment this solid, the molecules are already vibrating. The moment heat is subjected to the molecules, they start vibrating more. So what happens when they vibrate more is the molecules gains energy and they tend to move away from each other. So when they move away from each other, the space between the molecules increase, due to which the object starts becoming a little bit bigger. Okay. So what is kinetic energy? The energy possessed by an object, a molecule, any particle when it is in motion. Right? So that is why cricketer also, when he has to bowl, he runs, comes, bowls. Why does he have to run? Because the speed of the ball will be more. If he's standing and throwing the ball and running and throwing the ball, the speed of the ball will be more when he is running. Okay, like a footballer, when he's taking a penalty kick, the football is kept up there. He goes back, runs, shoots. He's actually increasing the kinetic energy. Right? So, this is what happens on heating. The distance between the molecules increase, so the liquid, in solids, molecules are closely packed and held together firmly, so solids expand a little in on heating. Okay, but what happens in liquids? Liquids, the molecular distance is a little bit more than in the solids, right? So if in the solids the molecules are this way, in liquids are a little bit apart. So what happens is in liquid, when you start heating, the molecules start moving away from each other. So the liquid expands. That's why the milk boils over when you're heating it on a flame, over a flame, right? When water also, when you heat it from down, if this is a container and water level is still there, when it starts boiling and all, it comes right up. Okay. Gases, molecules, they are very far away from each other. There's hardly any intermolecular force of attraction. There is a huge intermolecular space between the molecules. So gases, when they get heated, they move away even more vigorously. Okay. It says in gases, molecules are free to move and the force of attraction between them is almost zero. So gases expand the most on heating. Okay. Now, types of thermal expansion. There are three types of thermal expansion, namely linear expansion, superficial expansion, and cubical expansion. So, the first one we are going to deal with is linear expansion. What does this mean? The increase in length of a solid on heating is called linear expansion. Increase in length of a solid when it is heated is called linear expansion. When the length increases, okay, make this very clear. There are three types of expansion, it's different. Original length of the solid, that's what the book says. A longer rod of a metal expands more than a smaller rod of the same metal when heated for the same amount of time. That's true. Longer rod will expand more than the shorter rod. Okay, for the same metal, the same type of metal for the same amount of times, same amount of energy. Okay. Now, increase in temperature. When two rods of the same metal having the same length are heated to different temperatures, the rod heated to a this is true. Two rods, same metal, of course, same substance. I will not say same metal, same substance, same length, but heated to different temperature. Let's say this is heated more and this is heated less. This will expand more than this one because of the difference in temperature. Okay. Now, nature of the solid, matter of the solid. What is the solid made of? That's what's called nature of the solid. When two rods of different metals having the same length are heated to the same temperature, one rod expands more than the other depending on the nature of the metal. Okay, out here also, it depends on the density of the metal. Okay, how dense or how less dense or how more dense a solid is. Okay, so it depends upon what it is made of, what is the composition of the solid. So when the same temperature is applied to the two different solids of different materials, one will expand more, one will expand lesser. Okay. Now, superficial expansion. Expansion in area of a solid on heating is called superficial example. For example, the area of a plate or a sheet of metal increase on heating. Let's say this is a sheet of metal, thin sheet of metal. When it heated, it starts expanding, right? So the area starts expanding. This is called superficial expansion. Okay. Now, the third type of expansion that we have is cubical. It's from the wood. So this one is superficial. Number two is okay, where the area increases, and number three is cubical. So the word itself cubicle, should give you a hint. And cubical expansion, expansion in volume of a solid or liquid or gas is called. In the volume of a solid or liquid or gas expands or becomes bigger or increases. It's called cubical expansion. Okay. Now there is an activity in page number 84. It is called thermal expansion of solids. They are talking about it's called the grape sands ring and ball experiment. So what happens is there is let's say there is a ring and there is a ball. Okay. It's a metal ball, not any ball. Okay, so this ring is there, a metallic ring only, because we are dealing with heat and all. Okay, so what happens is initially when you take this ball and put it through this metal ring, it passes through, it goes through, comes back and all, right? But after some time, let's say you heat this ball. This ball is subjected to heat. What happens is you take first you put it through, right? It goes through. Then you take the ball out. Then you heat it. Then again you try to put the ball back into the ring. The ball will not go through. When you try to put the ball through the ring, it will not go through. What is happening? Simple, children. It's simple. The rim of the ring remains the same. It's not subjected to heat, right? So initially the ball it was in its original volume, original dimension, original size. So it would go through. But when it was heated, obviously it's a solid. So I said thermal expansion. That's what we're talking about. The solid expands. It becomes bigger. So second time when you're trying to put, initially when the ball was going through the ring, it was fitting exactly. But second time when it gets heated, it becomes a little bit bigger. That's why it's not going through. Okay, let it cool. Give it some time. Let it cool. When it cools down, again it will go through. Okay, it's a very simple experiment, and it's called Grapesands ring and ball experiment. Okay, so different substances of identical dimensions with identical sizes and all, when heated to the same range of temperatures, expand by different amounts, as I've already told you. Okay? For example, brass expands 1.5 times more than steel, right? And aluminum expands twice as much as steel. So let us perform an activity. Again, activity 2, this is called to show the relative expansion of different solids. It's basically got a bimetallic strip. So okay. So this is called a bimetallic strip. One part is iron, one part is brass. They've been put together. They've been glued together, put together, riveted together, whatever. Okay. What happens when these bimetallic strip or these kind of bimetallic strips are subjected to heat? Let's say they are subjected to heat, right? They are subjected to heat. All this is heat, right? This is heat. So when they are subjected to it, what happens? Okay. After some time, you'll realize that this bimetallic strip becomes somewhat like this. Curves up. If the brass is below, if the brass is up, it will curve down. What is happening is when heat is subjected, both of them start expanding. But the brass expands more, as I've told you already. Okay, in fact, if I don't put iron out here, if I put steel, it's given in the book, it says brass expands 1.5 times more than steel. So if you put steel out here and brass, this will start curving upwards. Why? Because the brass expands more. and the steel expands lesser with the same amount in the same amount of time but the same amount of temperature. Okay, so if they were not riveted together, the steel would have looked like this after some time, and the brass would have looked like this if they were not put together. Okay, if they were put separately, But since they are put together, they are trying to expand together. The brass expands more, the steel expands lesser. So in order to do that, since the brass cannot go forward, it starts bending. This is what happens. Okay, a very important thing used in automatic fire alarms. We'll be talking about that. Okay, it's a very important device. If there's a fire in a house, a fire in any place, this automatic fire alarm goes off. Then the water goes off. Fire department is alerted. Catastrophe can be avoided. Lives can be saved. So many things, right? So all these things, simple children. It's all simple physics. Okay. Now, examples and applications of whatever that we talked about, thermal expansion of solids. Okay. Thermal expansion of solids has many useful expansions in daily life, though in some cases it can be disadvantageous too. True, if something has its merits, it will have its demerits also. Some of the examples and application of thermal expansion in our day-to-day lives are given here. Horse carts and bullock carts are wooden wheels. Okay, I don't know how applicable this example would be in today's life, because when I was a child, in our times, we saw a lot of them. They are called tongas also. I think certain place, I don't know exactly which region, but we people adults, when we move down to the plains, we see this, because in the hills we hardly see any bullock carts or anything like that anymore. Okay, when I was small, I used to see, but now we don't see it anymore. Life has become totally different, right? So if you go down to the plains, you call them tongas. You see this horse-driven cars, bullock cars, like you movie Sholay, famous movie Sholay. You children, you will. It's a very old movie. I was also small. I think I was in my mama's lap when the movie was released. Basanti or Hema Malini is uh, Dhanno is I think that horse which she pulls the cart. You know, those carts were very famous in India. I think if you go to Victoria Memorial in Calcutta, they still have those carriages where it's pulled by horses, right? So this wheels are actually, it's a wooden wheel. Okay, it's a wooden wheel. See, it's very difficult to get a round piece of wood, like this, right? In this shape, it can't. You'll have to put pieces of wood. In fact, you'll have to shave off and make it into a curve, and you have to put them together, right? Now, let's say this is put on the wheel of a bullock cart or a horse-driven cart. Okay, so we are moving on the road. What if one piece falls off? Or what if one piece comes off and the cart is at a good speed? In fact, before the invention of cars, before the cars were born, before we introduced the cars, the world used to move on horses and horse-driven cars only, right? Wild West and all, stagecoach and all those things, right? So what happens if one part comes off? Number one, if it's not moving, they'll have to repair it. It'll take time. If it's on a high speed, the whole cart will topple, and people might lose their lives. An accident will take place. Okay, that's how dangerous it is. Now, how do you solve the problem? How did people in those times solve the problem? So what they would do is, they would put a metallic strip around the wooden wheel, and the metallic strip would hold the wooden wheel together. They would bind it together. But how? Doesn't the metallic strip also come off? Okay. So what they would do is, if the wheel was of this dimension, they would take a metallic strip which is a little bit smaller. Right? Now, they would heat this metallic strip. Okay. Heat. Heat would be provided to this metallic strip. When it is heated, red hot or whatever, it would expand. Understood? It will become bigger now. Okay? So it will become big. It will expand and it will become bigger. Now when it becomes big, they take this off and they put it over the wheel. Right? They pick it with the fire tongs or whatever. They put it over the wheel. Then they start cooling it. Or either they put water or they let it cool naturally. But most probably they would put water and cool it. So when it cools, when it starts getting cool, the metallic strip will try to go back to its original size. Okay. In doing so, initially it was smaller than the rim of the wheel. Okay. Now it has become big because it was heated. So when in the heated state it is put over the wheel, and water is poured over it, it starts contracting, tries to go back to its original size. In doing so, it binds the wooden wheel together. Okay. So now it is much more safe, much more convenient, much more reliable, the wheels, so that you can move around. Okay. But in hot places, when these kind of horse cars or bullock carts were used on the roads and the roads were really hot, the tarmac was hot, or if we are moving over cobbled streets, if it's hot and all, what they will do, the stronger drivers, they always carry cold water with them, or wherever they get cold water, they'll stop the cart and they keep pouring cold water over this wheels. Okay, they're trying to cool down the metal, because if it gets heated, the metal will expand more and more. Again, if it becomes so big, it might just come up. Again, there will be an accident, right? So they keep stopping time and again, cooling the metal, so it keeps the wooden wheel binded together. Okay, now second one, railway tracks. If you've seen railway tracks, there are gaps between railway tracks. Okay, the beams, the pillars of railway tracks that are used, will always be at, if this is a railway track, okay, and not too good at drawing, children. I'm just trying to explain. Okay, so they are wooden sleepers in the middle, right? And these are the railway tracks. Though they are bonded together by a small piece of metal, there's a gap in the middle. Okay, why do they keep gaps? Right? The gap is not so big. Okay, not so big, it's a small gap. Why do they do that? Railway track again is made of solid metal, the railway tracks. Okay. Thermal expansion, metals get heated. When they get heated, they start expanding. In hot places in India or all over the world, they are very hot places also. Right? So when the tracks get heated, if they expand, if there's no gap left in the middle, what will happen to the tracks? They'll become like this. Imagine a train is moving at fast speed, at top speed, and the track has bent in the middle like this. What will happen? It's not a car. Okay, if a car has a bump on the road, it will just go over and come down. But if a train meets this bump, this train will come, and with the bump, the train will be a plane for some time. After that, when it crashes, then you know what will happen, right? So you have to avoid that accident. For that reason, there are gaps left in the middle, right? So in winter again, as it becomes colder or as the temperature starts going down, again the railway tracks goes back to its original size, but there are clasps in the middle which holds them together. Understood? These are very simple explanations, children. You should, next time you go on a train, you should always watch the railway tracks and you'll understand what I'm trying to tell you. Okay. Iron girder used to make a bridge is fixed at one end while its other end rest on rollers. The end resting on rollers is free to expand in summer and contract in winter. Basically, what they're trying to tell you is, if a bridge just make a simple bridge. Okay. One part of the bridge is fixed onto the wall, or whatever part it is, right? The other part of the iron girder, the main girder, this is the girder. The main girder of the bridge, there are rollers on it. We cannot see it has been constructed in such a manner, and there is a space. Okay, some amount of space is left up there. Why would you do that? In summer, when it gets heated, this girder expands and this bridge will go, okay, and try to cover up the space. And when it is moving, these rollers are there which will help it move smoothly, okay. And when it becomes cooler, as winter comes, again it will try to go back to its original size, and rollers again will help it move. Now, let's imagine that we have fixed it together like this, and there's no space left, there are no rollers for it to move. What will happen to the bridge? In summer, when the metal will try to expand, it will try to go this side, there's no space. It will try to go this side, there's no space, and suddenly you'll realize instead of a straight bridge, you'll have a bridge like this. Again, very dangerous, okay. It may not be up to the specification, accidents and all these things may happen. Okay, these are very common things that, see, whatever I'm talking about is engineering, okay. These are all concepts used in engineering. These are one of the things that are taught in engineering, right? But again, what class are we in right now? Class 8. The concept of engineering are taught to you earlier in the classes. So if you understand all these things right now, later on if you pursue engineering, it will be easier for you to study, right? Okay. Now, telephone and electric wires. Everybody's seen telephone and electric wires, the electric poles, right? The wires have been put, okay. There is a way to put it when you put it in summer. There's a way to put it when you put it in winter, okay. Now, in this book, I've only talked about telephone and electric wires always kept loose between utility poles. It is done to prevent them from snapping in winter. They just talked about the winter. I'm going to expand it a little bit more. When wire has been put between two poles in summer, it becomes, you have to put it a little bit loose, not so loose that it will go down to the touch the ground. It becomes dangerous. A little bit loose. Why? Because summer the wire is in an expanded state. Okay. So when the summer goes off, when winter comes and it becomes cooler, the wire will start contracting and go back to the original size. So when that happens, they will be a little bit tight. Okay. So when it is laid in winter, it is not laid loose. It is laid perfectly exactly the way it should be, so that in summer when it becomes hot, the wire will become a little bit loose. So in winter, if you let it loose, what will happen in summer? It will expand more, it will become so loose that it will come to the road and people will get electrocuted, accidents, so many things. Okay, there was a recent video on Facebook and all where a wire was pulling a person, a lady, a very dangerous situation. Okay, and similarly, in summer, if you lay it too loose, right, in winter it will not contract enough, right? So it again become a catastrophe. So these are all practical examples that we do. Okay, so children, will be continuing from that point onwards. I'll be doing more. I think I just need one or two classes with you to complete this chapter. I think one class should do. The next class I'll try to finish it off. Okay. In the meantime, notes are there. Please go through it. If you have any issues, do let us know. Thank you, children.